Why we've never explored above the sun. Every map of the solar system you've ever seen hides something important, not because the maps are wrong, but because they quietly leave out one of the most unexplored regions in our cosmic neighborhood. When most people imagine space, they picture a vast, three-dimensional ocean stretching endlessly in every direction, planets floating above us, below us, and all around us. The reality is surprisingly different. Almost everything in our solar system moves within a relatively thin, flat disk surrounding the Sun. Mercury follows it, Venus follows it, Earth follows it. Mars, Jupiter, Saturn, Uranus, and Neptune all orbit within roughly the same giant cosmic plane. For more than 60 years, humanity has explored that plane. We've sent robots to Mars, we've landed on comets, we've flown through the rings of Saturn, we've visited Pluto, we've even launched spacecraft so far from Earth that they are now drifting through interstellar space. Yet one direction remains strangely untouched. Not farther outward, not deeper into the darkness between the stars, but straight above the sun. And the reason why reveals one of the strangest challenges in all of space exploration. To understand it, we need to forget almost everything our intuition tells us about motion. Because the greatest obstacle isn't distance, it's momentum. At this very moment, Earth is racing around the sun at approximately 67,000 miles per hour. That's fast enough to travel from New York to Los Angeles in less than 3 minutes. Every human being on Earth is moving at that speed right now. We simply don't notice because everything around us is moving too. The atmosphere, the oceans, the ground beneath our feet. When a rocket launches from Earth, it inherits that motion automatically. The spacecraft doesn't begin its journey sitting still relative to the sun. It's already moving sideways around our star at tens of thousands of miles per hour. Think about standing in the back of a speeding truck. If you throw a ball straight upward, the ball doesn't land behind you. It continues moving forward with the truck. Spacecraft behave exactly the same way. The moment they leave Earth, they carry Earth's orbital velocity with them. Most of the time, that's extremely useful. Mars is moving around the Sun in roughly the same direction as Earth. Jupiter is too. So are Saturn and Pluto. The spacecraft simply adjusts its orbit while continuing to travel around the Sun. But reaching a point directly above the solar system is different. Now the spacecraft must fight against the motion it inherited from Earth. Instead of traveling around the sun, it must begin moving almost perpendicular to the entire planetary system. And changing direction in space is incredibly expensive. In orbital mechanics, velocity changes are measured using something called delta V. Engineers obsess over delta V because every additional meter per second requires more fuel. A small change in direction can demand enormous amounts of energy. A 90-degree change can become extraordinarily costly. In fact, sending a spacecraft high above the sun can require more energy than sending 1 billion of miles outward toward the edge of the solar system. That's why humanity reached Pluto before properly exploring the sun's poles. The irony is almost unbelievable. The closer destination turned out to be the harder one. And that left scientists with a major problem. For decades, we knew remarkably little about the sun's polar regions. Imagine trying to understand Earth while only observing countries located near the equator. You would never see the Arctic. You would never witness polar storms. You would never understand how heat circulates around the planet. Your understanding would always remain incomplete. The same was true for the sun. Researchers suspected the poles played a crucial role in controlling magnetic fields and solar activity, but no spacecraft had ever seen them directly. Then came a mission that would change everything. Its name was Ulysses. Launched in 1990, Ulysses faced an impossible challenge. The spacecraft simply didn't carry enough fuel to tilt its orbit dramatically enough to reach the sun's poles. So engineers devised an ingenious solution. Instead of using rocket engines, they would borrow gravity itself. The spacecraft traveled for years toward Jupiter. At first glance, this seemed absurd. Why travel farther away from the sun if your goal is to study it? The answer lay in Jupiter's enormous mass. As Ulysses approached the giant planet, Jupiter's gravity grabbed hold of the spacecraft and bent its trajectory. The maneuver acted like a colossal, cosmic slingshot. Without burning huge amounts of fuel, Ulysses suddenly found itself traveling in a steep orbit that carried it far above and below the plane of the solar system. For the first time in history, humanity could observe the sun from a completely different perspective. What scientists discovered was fascinating. Powerful streams of charged particles were blasting outward from the polar regions. Magnetic structures stretched across millions of miles of space. The sun looked far more complex than researchers had imagined, and yet Ulysses also revealed how much remained unknown. Its instruments were revolutionary for the time, but technology would continue advancing long after the mission ended. Eventually, Ulysses fell silent, and once again the poles of the sun became one of the least explored places in the solar system. Years later, another spacecraft would continue the journey, the European Space Agency's Solar Orbiter. Unlike previous missions, Solar Orbiter carried advanced imaging systems capable of photographing the sun in extraordinary detail. But even this mission couldn't simply point itself upward. Instead, engineers used repeated gravity assists from Venus. Each flyby subtly tilted the spacecraft's orbit. A little more, then a little more, then a little more. Over years of careful navigation, Solar Orbiter slowly climbed above the ecliptic plane, and eventually, humanity witnessed something no one had ever seen before: the sun's south pole, directly. The images revealed strange magnetic structures unlike anything visible from Earth's perspective. Scientists hope these observations will help solve one of solar physics' greatest mysteries. Every 11 years, the sun's magnetic field flips. North becomes south, south becomes north. The process influences solar storms throughout the solar system. Yet researchers still don't fully understand how the reversal begins. The answer may lie at the poles, but the implications stretch even farther than the sun itself. Because the solar poles may help explain the shape of the heliosphere, the gigantic bubble created by the solar wind that surrounds our entire solar system. For decades, scientists imagined this structure as something resembling a comet with a long tail stretching behind the sun. Then new data began challenging that picture. Some researchers now believe the heliosphere may look more like a giant cosmic croissant. Strange as that sounds, observations suggest the powerful streams emerging from the sun's poles could be shaping space on scales that are difficult to comprehend. And to understand that process, future missions may need even more extreme trajectories. Some concepts involve enormous solar sails. Unlike conventional spacecraft, these vehicles would use sunlight itself as propulsion, photon by photon, day after day, year after year. The pressure of sunlight would slowly push the spacecraft into increasingly unusual orbits. The process would be slow, painfully slow, but incredibly efficient. Other mission concepts are far more dramatic. They rely on one of the most extreme ideas in astronautics, the Oberth maneuver. Named after German physicist Hermann Oberth, the concept takes advantage of a surprising fact about orbital mechanics. Rocket engines are most effective when a spacecraft is already moving very fast. So instead of accelerating far from the sun, engineers could send a spacecraft diving toward it, closer, closer, and closer still. As its speed increased, the spacecraft would fire its engines at precisely the right moment. The result would be a tremendous boost in energy, enough, potentially, to launch it into trajectories impossible by conventional means. It's one of the strangest ideas ever proposed. To travel above the sun, you might first need to fall toward it. The shortest route upward may begin by heading down, and perhaps that's the perfect metaphor for exploration itself. Again and again, the universe forces us to abandon common sense and embrace ideas that seem completely backward. Yet every time we do, we discover something extraordinary. Today, the regions above and below the sun remain among the